In this video, we're going to introduce a convergence test that's known as the alternating series test. The alternating series test is only able to determine if a series converges. You will never say the series diverges by the alternating series test. So what we start off with a sequence. All of the terms are positive. Now we're going to actually throw those positive terms, throw negative signs in front of some of those positive terms, but that's for later. We also know that the terms form a non-increasing sequence. Non-increasing means kind of like decreasing, but they get smaller as we go. Maybe every once in a while we have equality, but they get smaller. They have to get smaller because the limit of these terms has to go to 0. So we have positive values, kind of decreasing, and the terms go to 0. And then we're going to take the first term minus the second term plus the third term minus the fourth and so on. So all the b sub n's are positive. This is going to look like something minus something plus something and so on. Let's look to see what happens with the partial sums. So we start here at 0. And I'm going to look at the first partial sum. Well, the first partial sum is just b1. Okay? So it's just b1. And notice that that gets us to s1. Now, the second partial sum, remember we went b1 minus b2. So for the b2s, for the even b's, I've done a negative. So we're going to come back this way, which gives us the second partial sum of s2. The third partial sum will be b1 minus b2 now plus b3. So we're going to add back in and we're going to end up back here, which ends us up at s3. And then we subtract b4. There's our fourth partial sum. And we add b5, which will give us our fifth partial sum, just to give you a sense as to what's going on. So you can see that the red ones go S2 is less than or equal to S4, which is less than or equal to S6, and so on. On the right side of things, S1 starts off at the highest, then S3 is next highest, S5, and so forth. The even ones form an increasing bounded sequence, a sequence that's bounded above. Wait a minute, how do I know it's bounded above? It's bounded above because, well, S1 is going to be larger than any of those. Since it's increasing and bounded above, it converges. Similarly, S1 through S1, S3, S5, and so forth is decreasing and bounded below by 0, and so that sequence is going to converge. Now here's the great thing. If we look at the difference between consecutive terms in the sequence of partial sums, we're going to look at s sub n plus 1 and s sub n and find out how far apart they are. Well, let's take an example here. Let's suppose that n is equal to 3. So if n is 3, we're here at s3. s4 is down here. The difference between them is how far apart they are. Well, they are this far apart. Now, if we look down, straight down here, bingo, we hit there. And we look straight down here, bingo, we hit there. So the difference between S3 and S4 is equal to B sub 4. It's equal to the larger of, or it's equal to B sub whatever the larger subscript is. And we know that the B sub n's go to 0. That was one of the conditions. These guys went to 0, and so they will converge to the same value. Not only do these guys converge, they'll converge to the same value, which means that some number in between these guys, we'll color it blue here, some number in between them will be the limit. But wait, there's more. Okay, so let's look at the sequence of partial sums. It goes b1 minus b2 plus b3. So we either have the actual value of the sum is between Sn and Sn plus 1, where Sn is smaller, or it's the other way around, where Sn is larger. Okay, so the value of the sum, just as we said, has to be between them. And so the value of here's the great thing. The value of the actual sum, the value S, is no farther from S sub n, the nth partial sum, than the b sub n plus 1. Let me say that again. If I take the nth partial sum, how far am I from the true value? Well, the true value is trapped between S sub n and S sub n plus 1. That distance is b sub n plus 1. So the maximum error we can have by taking the nth partial sum is the first term that we don't include in the sum. So here's the alternating series test. We'll talk about that last bit in a bit, okay? Same sort of thing we were talking about before. We have a sequence of terms where it's non-increasing. The terms go to 0. And then we alternate the signs. A positive number minus another positive number, plus a positive minus a positive. All of these values are greater than 0. This series is convergent. We have to know, though, that it's decreasing or non-increasing, and the terms go to 0. Okay, so there are kind of 3 things that we should list here. We should list that it's an alternating series, the terms are decreasing, and they go to 0. Now, when we talk about the terms, we're talking about everything without the negative 1 to the n negative 1, or negative 1 to the n, or negative 1 to the n minus 1. So for our first example, let's look at this particular sequence, or series. We're going to look at n goes from 1 to infinity of negative 1 to the n minus 1 over n. Now I'm actually going to write these out because this should be kind of familiar. When n is 1, the denominator is 1. And the numerator will be negative 1 to the 1 minus 1, or negative 1 to the 0th, which is positive 1. The next term has a denominator of 2. The numerator is negative 1 to the 2 minus 1. 2 minus 1 equals 1. Negative 1 to the first is negative 1. And then we'll see that these will alternate in sign. Minus 1/4, plus 1/5, minus 1/6, and so on. Now, you might recognize this and say, hey, that looks like a cousin to a favorite sequence, a series. This looks like the harmonic series, and it is known as the alternating harmonic series. Okay? So I want to fit it to the alternating series test. So I'm going to let b sub n be what each term looks like without the negatives. So b sub n is the sequence 1 over n. It is decreasing. Is it? Well, sure, because if n gets bigger, the denominator gets bigger, so the fraction gets smaller. It's decreasing. The terms go to 0. It's decreasing, it approaches 0. And my series is alternating. So what that means is by the alternating series test, the series converges. You can see we had to do very, very little work there. We just had to confirm that the terms went to 0, the terms are decreasing, and the series is alternating, and we can conclude that it converges. Now, I'm not going to tell you that how I know this right now, but it turns out that not only does it converge, but we actually know what it converges to. This series, negative 1 to the n minus 1 over n, converges to the natural log of 2. That's just strange, but it's true. Okay, let's look at part B. I see that we're going to have an alternating series because of the negative 1 to the nth. When I remove that, I'm going to block it out here really quick. When I remove that, the terms that remain are positive. Okay, so let's go ahead and we'll let b sub n be what's left. 1 plus n over 1 plus 5n. If b sub n is decreasing and approaches 0, then the series converges. Okay, so let's look at this. As n goes to infinity, 1 over n plus 1 over 5, or over 1 plus 5n, 1 plus n over 1 plus 5n. Well, for large values of n, the numerator and denominator both approach infinity, so I can take only the most exciting terms, the ones that are larger, n over 5n. Hey, that reduces to 1/5. In order for us to use the alternating series test, the terms have to go to 0. Okay, they don't go to 0, so I can't use the alternating series test. However, I just invoked a different test. The terms do not go to 0. The series will diverge by the divergence test. Okay? So that's kind of an interesting little byproduct of this. Sometimes we'll look at a series and we'll say, hey, look, it's alternating. Let's check to make sure that the terms go to 0. Oh, wait, they didn't go to 0. Oh, when they don't go to 0, that means it's going to diverge using the divergence test. Okay? So the alternating series test and the divergence test kind of compete for these series. Hey, I'm going to take one that converges. No, I'm going to take one that diverges, and so on. Okay, let's look at part C. In part C, I'm going to let B sub n. I do notice that it is alternating in sign because of the -1 to the nth. You might see -1 to the nth, -1 to the n plus 1, -1 to the n minus 1. You might also see a really obnoxious thing like maybe the cosine of pi times n. That would be just cruel, but it could slip in there. But I notice that it's an alternating series. And so I'm going to let B sub n be the terms without that -1 to the nth. So it's radical n over n squared plus 1. These terms are all positive. And so I want to know, do the terms go to 0? Well, the denominator has a power of n squared. The numerator only has the square root. N squared overpowers the square root of n. So this approaches 0. And, I'm going to do some kind of hand-waving stuff, and is decreasing. Really? Is it? I don't know, but I think so. Okay, what I would do is I would confirm that it's decreasing using a graph, or if I'm so brave, and I don't think this one looks very pretty to do this with, use derivatives and show the derivative is always negative. So the terms approach 0, and the terms are negative, or are decreasing, so the series converges. By the alternating series test. Okay. Later, we're going to look at things called power series. And when we do power series, we do some strange stuff where we figure out when the stuff will converge. There's a variable in our series. Instead of just having formulas for n's, there was a variable x. So we'll figure out sort of a range of values on which it converges, and then we'll have to test at endpoints, whatever that may mean for right now. This alternating series test often pops up in that, so it's a really powerful and useful test for us. We have something that's known as the alternating series estimation theorem, which we talked about at the very beginning of this. All right, so let's suppose I want to approximate the value of an alternating series. I know it converges. About how much, or about what number does it converge? Well, we would do partial sums. Okay, so the way the theorem runs, it says if the sum is the sum of an alternating series, again, where the terms are non-increasing and the terms go to 0, then the remainder, we talked about the remainder in the integral test video. The remainder is how far we are from the actual value of the sum. It's always going to be less than or equal to b sub n plus 1. So I really emphasize this. If you do a partial sum, the nth partial sum, how accurate am I? Well, I'm only as accurate as the first term I didn't include in my sum. Okay, so we're going to estimate this series accurate to 4 decimal places. And the series is -1 to the nth. This one's kind of funny because we're starting at n equals 0 this time, but it's negative 1 to the nth, so I know it's an alternating series. Not only is it an alternating series, but the terms are going to go to 0, so b sub n would be 1 over 3 to the nth times n factorial. Certainly that denominator gets large really fast, actually. Large, fast, and the terms will go to 0, and they're decreasing. So it does converge by the alternating series test. Okay, let's write out several of these terms. Okay, so I'm going to start at n equals 0. I'm going to compute things as I go, so be careful. Remember that n factorial, if you've never seen factorials, n factorial is the product of all numbers from n down to 1, all whole numbers. Or if you want, you could say it's the product of all numbers from 1 up to n. So for example, 4 factorial is equal to 4 times 3 times 2 times 1, which is 24. We define 0 factorial to be equal to 1. Okay, there are some excellent reasons for this, but we define it that way, and there are excellent reasons for defining it that way. Okay, so I'm going to write out the series, and we're going to play around with this. So when n is 0, I have negative 1 to the 0th, which is positive 1. 3 to the 0th is 1, and 0 factorial is 1. So we're just going to end up with positive 1 for the very first term. Minus. Now when n is, okay, now I've jumped the gun. When n is equal to 1, negative 1 to the first is negative 1. That's where the minus comes from. And the numerator will be 1. And then in the denominator, we'll have 3 to the first, which is 3, times 1 factorial, which I'll just say is 1. When n is 2, negative 1 squared is plus, so we'll have 1 over 3 squared times 2 factorial. And now you can see the pattern, I think, minus 1 over 3 cubed times 3 factorial plus 1 over 3 to the 4th times 4 factorial minus 1 over 3 to the 5th times 5 factorial, and so forth. Okay, so I want to estimate this accurate to 4 decimal places, which means I could take a partial sum. If I want to, I could go ahead and erase just the last little bit there. Maybe I could calculate that. That would be like, I guess, the 6th partial sum, since we have 6 terms. Okay, I don't know. Maybe I need to go farther. So I'm going to put a plus dot 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 here. In order to be accurate to 4 decimal places, that means we don't want to have problems with rounding. We probably ought to sneak a little bit into the 5th decimal place to make sure that we're like less than, halfway into that 5th decimal place, if that makes any sense. So what I'm going to do is I'm going to list here the computed decimal values for each of these terms. I've added an extra term. We'll see why in just a moment here. So here are the decimal values for each term. If I were to stop after the first 3 terms there, that estimate would be only accurate maybe up to 0.006173. So that could be the farthest that estimate would be off. If I add the first 4 terms, how far off could I be from the actual value? I could be 0.0005 off of the actual value. I want to be accurate to 4 decimal places. So if I look here at the 4th, where it's 1 over 3 to the 4th times 4 factorial, that's got a 5 in that 4th decimal place. That's too imprecise. Over here, I've got those 4 decimal places, but I've got this 3, which might make things bump up if I'm not accurate enough. Here, though, I've got 1, 2, 3, 4, 5 zeros, and then a 1, 9. So this is the worst error I would have if I include these terms. Okay. Whoops. I went too far there. There we go. So these terms, if I add these up, the greatest error that I could have is this 0.00000019. And so I'm going to erase, get rid of this guy, and I'll compute this partial sum. And this is approximately equal to 0.7165. Kind of neat. It's kind of a special way to estimate these things and know exactly how far off we are, or get an approximation of how far off we are. Okay, we're going to round out this video with a discussion of what we mean for something to be absolutely convergent. Now, we've been playing with these alternating series. So a series is absolutely convergent if, when we take the sum of the terms where we drop all of the signs, that series is convergent. Okay, so in order to be absolutely convergent, we want to take every single term in our series, make them all positive. If they're negative, just change their sign to positive, add them up. If that series converges, it's absolutely convergent. If, on the other hand, those negative signs are doing something important for us, if they're keeping the tally down enough, if the series converges but the series consisting of the absolute values of the terms diverges, we say that the series is conditionally convergent. So we have absolutely convergent and conditionally convergent now. Let's look at an example here. Is this series absolutely convergent or conditionally convergent? Well, we already know that it's convergent. This was an alternating series. We called it the alternating harmonic series. So we learned that this guy converges in one of our earlier examples. Okay, so we now ask, is it absolutely convergent? Well, I don't know. Okay, well, let's check it out. I'm going to take the series, n equals 1 to infinity, take the absolute value of all this business, negative 1 to the n minus 1 over n. Negative 1 to any power is either negative 1 or it's positive 1. Okay? If you take the absolute value of negative 1 or the absolute value of positive 1, you get 1. And so this is the series n equals 1 to infinity of 1 over n. This is a good old friend. This is the harmonic series, which diverges. So the original series converged when we took the absolute value. We got a divergent sequence, so that we say this is conditionally convergent. Okay? It's conditionally convergent. So here's something that's interesting, and we're going to see why it's so interesting in this next example. If a series is absolutely convergent, then it's convergent. Okay? So wait. If I take a series and replace all the terms by the absolute values of the terms, and that series converges, then the original series was convergent as well. We'll talk about this after we do this next example. We want to know if this series, where we have the sine of n, that is weird, divided by n radical n, is it absolutely convergent, conditionally convergent, or divergent? All right. Well, I don't know. Let's check it out. I'm going to see what happens if I take the absolute values. So let's look at this. Sum n equals 1 to infinity, absolute value of the sine of n over n radical n. Okay, let's just look at the terms. And the reason I'm just looking at the terms themselves, you'll see in a moment. The only way this could be negative is if the sine of n is a negative number. Okay, so I'm going to put the absolute values around this absolute, or around the sine of n. Okay. And what I know here is that the sine of n, an absolute value. If I graph the sine, remember it goes something like this. Ooh, that was a horrible graph, but you know what I mean. It varies between positive 1 and negative 1. So in absolute value, this is going to be less than or equal to 1 over n radical n. Now that is 1 over n to the 3 halves. Okay. Well, let's think about the series of n to the 3 halves. 1 over n to the 3 halves. This should look like something we've talked about before. this is a power series or a p series. The p is equal to 3/2, which is bigger than 1, so it converges. That's interesting. So what? So what, you say? It converges. So if we have any sequence that is smaller, or any series consisting of terms that are smaller than it, that will also converge. And lo and behold, back here, the series that we were looking at is less than or equal to that series. And so by the comparison test, the series that we were looking at, the absolute value of the sine of n over n radical n, converges. But wait, there's more.